Hello guys, I'm Arshavadni and I'm going to explain the ideal gas law in food, how food expand and shrink. These are some of the foods which obeys ideal gas law. Have you ever made waffles? Have you experienced that thrill when they rise high in the oven, looking so beautiful and light, but to be heavily disappointed when they sink down again once they're cooling down outside the oven? Have you seen a cake lift in the oven? If so, you've seen the ideal gas law at work. Gases shrink and expand all the time when you're cooking and baking. And knowing just how this gas law works and can get a minimum help of you explain your fellow eaters why those waffles collapsed or even help you prevent them from collapsing completely.
Phase changes from solid to liquid to gas. Gases might remind you of the oxygen we breathe around us or the carbon dioxide that comes out of our carbohydrates. But that vapor about your boiling hot cup of tea is a gas too. All those air bubbles within your bread are also filled with gas. Unlike in a solid where all molecules are fixed in place or a liquid where molecules do pull one another, molecules have a lot of freedom in a gas. So much so that they'll distribute themselves in whichever space they are trapped. This could be within an air pocket in a bread dough or within a pot of boiling water.
Let's see what ideal gas law is. This independent behavior makes gases do interesting things, and those things can be described using the ideal gas law. As the name says, this law describes the behavior of an ideal gas. The ideal gas law describes how gases behave under varying temperatures, pressures, and volume. It can be expressed by a quite simple formula: PV is equal to nRT, where P is pressure, V is volume, N is number of molecules, R is gas constant, and T is temperature in terms of Kelvin. This formula tells you if you multiply the pressure of a space that the gas is with the volume of that space, that outcome is identical to a multiplication of number of gas molecules present, a specific constant, and a temperature. In the oven, temperature increases as such nRT becomes a large value. As such, PV should also become larger. In this case, that will result in an increase in volume. The gas within that bubble expands because of the heat. These types of changes in a temperature occur in food all the time, and even the number of molecules may change as may the volume. The following examples bring some of the scenarios to life. Before that, we'll see why aren't real gases ideal. In the ideal gas law, scientists make a few assumptions about the gas. First, they assume that the molecules make up gas do not have any attractions between one another, and secondly, they'll assume the gas molecules themselves don't actually take up any space. In real life, both assumptions aren't correct. We stay pretty close to those normal conditions, making the ideal gas law useful too. Ideal gas law, example 1, taking a sulfur. Imagine a vessel of 1 meter cube at 300 Kelvin and a pressure of 100 pascals. With close of 40 moles of gas inside, we'll heat the vessel, which contains sulfur batter, which are very delicate and soft. They tend to contain a little fluffy egg whites full of gas bubbles. Let's heat this batter to 400 Kelvin. You might expect the vessel to cool off. However, this sulfur batter isn't as firm as a liquid vessel. The sulfur batter can't hold its shape under an increased pressure, so we have to assume the pressure within the sulfur remains the same, that of a surrounding air. So what will happen? The volume will increase to 1.3 meter cube. The sulfur batter has grown in size. It started out as 1 meter cube. One great challenge with waffles is always to prevent them from collapsing if you take them out of the oven. Unfortunately, this only works if your waffle is rigid enough to hold its shape and resist that change in pressure. A waffle, even a cooked one, has a very delicate structure and can't handle this. The decrease of temperature will therefore always result in at least some volume decrease.
Let's see another example of ideal gas law, that is baking a cake. In a lot of foods, the number of gas molecules in a food isn't constant. When baking a cake, popping a popcorn, or baking a souffle, new gases will be formed. Water might evaporate into gas, and leavening agents such as baking powder may result in the formation of carbon dioxide, and water will evaporate. So let's get back to the same scenario from the previous example. But in this case, it's a cake batter with 40 moles of gas and temperature of 300 Kelvin and a volume of 1 meter cube and a pressure of 100 pascals. We again increase the temperature to 400 Kelvin. However, this time a lot new gas molecules are formed, and thanks to the baking powder and evaporating water. This results in a total of 60 moles of gas molecules. Since the cake batter isn't very strong, it won't be able to withstand any higher pressure, so pressure will stay constant. As a result, the volume will have to change again, where it changes to 2 meter cube. See how much larger this cake is gotten compared to the previous example. A well-cooked cake batter is stronger than a soft one. As such, it will be able to withstand the temperature drop once taken from the oven, but only when it is well cooked. If you take a cake out of the oven too early, it can still collapse, causing it to lose some of those gases. Even if you put it back in the oven, the loss of those gases will make it almost impossible to get back its original size. The same for sulfur. Water in the sulfur will evaporate and become a gas and participate in this gaseous behavior. What's even worse, when taking the sulfur out of the oven, some of the water will condense again. This will contribute to the shrinkage of sulfur even further. Often, a whole lot processes play a role as well. Structures don't tend to be either super rigid or super flexible. Instead, most likely pressure, volume, number of gas molecules and temperature will all change simultaneously, or might start at the start of cooking process, whereas the others change towards the end. That said, though, you don't have to understand every single detail to still grasp these basic concepts.
Thank you.